All right, so Masanori is going to give us his second lecture on Monte Carlo techniques and all that.
Okay, thank you very much. So, at the end of my talk yesterday, I was talking about how to perform integral ABGM matrix model. And ABGM matrix model has several different representations. And probably most common form, which many people use for analytic purpose, is this. And here we have cosine hyperbolic square, sine hyperbolic square, sine hyperbolic square, but we have some exponential I times something. So now path integral weight is complex because of this factor. And I say the Monte Carlo simulation, at least usual Markov chain Monte Carlo can be applied when action is real. Or path integral weight exponential minus s is real positive. But now action is complex. Okay, so s are real part plus I times imaginary part. And the weight is now complex. And then how can we use Monte Carlo to study such system? Of course, in this specific example, just by changing variables like this, we can go to sign-free form, and we can do simulation. Okay? But in many cases, we don't really know how to get the sign-free form. And often we have to use this expression, which has a complex phase. And rather than complex phase, actually, even if there is no complex phase, if exponential minus s becomes negative, then already it's not a probability, and we cannot use Monte Carlo. So typically, this problem is called sign problem. Sometimes, when people want to emphasize that complex phase appears, sometimes people say phase problem, but they are the same thing. But typically, people call it sign problem. And still, in principle, so-called relating method can work. And very often people use this method. This is a kind of most straightforward, stupid way. So we want to calculate the expectation value of some observable, which is defined by this path integral. And the problem is this imaginary part of the action. But if you just look at exponential minus SB, this is of course real and positive. And we imagine as if this is a path integral weight. And then we can multiply this by 1. So we can just divide both numerator and the denominator by integral of exponential minus SB. Then numerator become expectation value of this operator times exponential minus is with this bosonic weight. This positive weight, exponential minus SB, and the denominator become phase of exponential minus is. And of course, we can calculate both by using Markov chain Monte Carlo, because now if we use this exponential minus SB as a path integral weight is real or positive. Then this way we can calculate any observable in principle, and if you want to calculate the path integral for partition function itself, then you just multiply this factor to this z, which is this factor times this expectation value. And you can calculate this integral just as before. So in principle, this way we can solve the sign problem, and we can still use Markov chain Monte Carlo. However, in practice, this exponential minus is, it oscillates very violently, and huge cancellation takes place, and it becomes really small, like 10 to the minus 5 or 10 to the minus 10. Typically, if you have, if you are trying to study some physical system with volume V, action is typically proportional to volume. So this imaginary part is also proportional to volume. Typically, you have to this combination, this expectation value is like exponential minus volume, which is really hard to calculate. So within error bar, it's almost 0. Then if you cannot distinguish this expectation value from 0 within error bar, you are essentially calculating 0 divided by 0, whose error is infinitely large. This is the sign problem. And there is no generic way to solve it. And this problem appears when we have a fermion. Okay, so action is bosonic part plus fermionic part, and the fermionic part is typically written as a fermion bilinear form. This is the Dirac operator. Then, because this is just a fermion bilinear, we can integrate fermion by hand. We don't really know how to put fermion directly on computer. It's not straightforward. At least we cannot do it efficiently, but we can integrate it by hand. Then this partition function. Okay, so suppose we have gauge field A and the fermion psi, and the bosonic part is just a function of the gauge field. Fermionic part is depend on the fermion and the gauge field. Gauge field is hidden in Dirac operator, and this part typically just give a determinant of Dirac operator. Then we just have to study so this gauge field is just a bosonic variable. So usual Markov chain Monte Carlo method can be used. We just have to regard this combination as path integral weight. So effective action is SP minus log of determinant. But the problem is this log of determinant is not always real. So determinant can sometimes become complex or negative.
But it's Hermitian,
very
Dirac operator is Hermitian.
Good. Or you would say action is real.
Yeah.
But the problem is action is real, or Dirac operator is Hermitian when in a Minkowski signature. When you go to Euclidean, you have to do Wick rotation. Then unitarity does not guarantee action is real. It just have to satisfy some other condition. Yeah.
Well, I have another question. This determinant of this kinetic term sometimes divergence. You need there's a function regularization.
But here, typically when we use Markov chain Monte Carlo by using lattice or some other method, we regularize it explicitly. So that's not a problem. Of course, when we take continuum limit, we have to deal with that divergence very carefully. We have to renormalize potentially divergent operators. But at regularized level, everything is finite. So this is the same problem. And for example, very luckily, in QCD, at least when we don't introduce chemical potential which couples the baryon number, we don't have sign problem. But in supersymmetric MELs, sign problem actually do exist. So determinant of Dirac operator is actually complex. However, somehow miraculously, that sign problem is not really a problem. So when we first tried the simulation of the supersymmetric matrix model of supersymmetric gradient theory, we thought that we will soon encounter sign problem and we just get stuck. That was we first thought, and we just tried anyway. But we noticed that, for example, at the high temperature region, fermion. So if you study a finite temperature system coupled to fermion, we impose anti-periodic boundary condition for fermion. And at high temperature, fermion has a very big thermal mass of all the temperature. So they are very heavy and compared to bosonic variables. So they are almost decoupled. So fermion's effect from fermion is very small. But then, of course, this determinant is effect of this determinant actually comes from fermion, right? And actually, at the high temperature, we can show that the determinant go very close to real and positive. And of course, when fermion becomes a bigger role at a low temperature, we don't really know, if determinant is still close to real positive. But somehow, empirically, to rather strong coupling region or rather low temperature region, determinants stay very close to real and positive. Then reweighting method can perfectly work. Or actually, we don't even have to do reweighting. We just ignore complex part and imaginary part of the action. That can still work. Very good approximation. And also, if we go to very low temperature, phase start to fluctuate a lot. We can observe that. But somehow, numerically, we can show that this reweighting method somehow works perfectly. So when this expectation value is still not too close to 0, we can do this reweighting by brute force. And then after reweighting, result doesn't change at all. And also, even when fluctuation is very big, we can see how fluctuation of the phase and the value of other observables are correlated. And actually, for important observable, like energy of the system, we can at least numerically show that the effect of phase is negligible. And we can just forget about phase. And we don't know why that happens, but at least numerically we can justify that. So far we do all simulation just by neglecting phase. And at least numerically we can justify that procedure. There is no analytic understanding about that, so if you can do that, it's very good. But somehow, mysteriously, for super MLs, phase sign problem is not really a problem. However, if you just do the same procedure, just ignoring complex part, to finite density QCD, for example, we know that at the analytical level, we already know that we get the wrong result. So it's very mysterious, but somehow it works. So we just take this strategy. We just forget about phase. So this way we can do perform Monte Carlo simulation. Once we have we define the theory. And next we have to see how we can define super MLs. And we want to define it in the way that we can actually put it on computer, in the way that we can apply Monte Carlo method. And the keyword here is lattice, and supersymmetry on lattice, and the fine-tuning problem. And in order to understand the fine-tuning problem, first of all, as a warm-up example, if we start with the pure Yang-Mills theory on lattice. By pure Yang-Mills, I mean 4-dimensional Yang-Mills just with gauge field, just bosonic degrees freedom. This is already very instructive example. And if you understand it, basically you can understand what is the problem with supersymmetry on lattice. And we start with the famous lattice gauge theory formulation by Wilson, which is called Wilson's placket action. So action is just like this. Here U is n by n unitary matrix, okay? And we have a 4-dimensional lattice. I can just draw 2-dimensional lattice, but you can imagine it's 4-dimensional. And from a point X, there are links extending to mu direction and the nu direction, and to all 4 directions. And the U mu X is a unitary matrix dealing on this side from X to X plus mu. And this U mu comma X is identified with exponential times I times lattice spacing A times gauge field at point X. And the coupling constant beta is inverse of 2/5 coupling. And of course, 2/5 coupling should run with a cutoff scale A. So we have to tune the coupling constant following the renormalization group equation. But anyway, if we take a continuum limit, so send A equals to 0 and tune the coupling accordingly, then this beta goes to this G Yang square times N becomes very small, like 1 over log N, and this beta becomes big, and this system becomes weakly coupled. We can this U can be regarded as 1 plus IA mu times higher order in lattice spacing. And then you can just expand it around 1, and you get this action up to higher order fraction. This is Yang-Mills action we want. And people use this formulation to study gauge theory on computer. But at first sight, when I first saw this formulation as a student, I wondered why we have to use such a complicated form. Why don't we use Hermitian gauge field? Why do we have to go to unitary variable? This is very crucial. Actually, that we use unitary variable here is very crucial because otherwise it's very hard to keep exact symmetries. Here by exact symmetry, I mean symmetries of a continuum theory, but exactly kept at regularized level. So continuum theory has gauge symmetry, rotational symmetry, translational symmetry, charge conjugation parity, and so on. And if you don't have symmetry, you don't really get the right theory. And we can write various different naive lattice action, which formally converges to correct theory at tree level or classical level. However, in quantum field theory, we have to take into account radiative correction. And if discretized theory does not have exact symmetry, then radiative correction does not have to respect such broken symmetry. And then we get some quantum correction which breaks such symmetry we want for continuum theory, and we end up in wrong continuum limit. Such thing can very often happen. And so we have to keep symmetry of the continuum theory in discretized level, at discretized level. So the most important thing is of course gauge symmetry, and this bracket action has this discretized version of the gauge symmetry. So we can multiply UN matrix living on site and its dagger at different points. So x and x plus mu hat means this point, x is here, x plus mu hat is here. And gauge symmetry, so gauge symmetry, a gauge transformation parameter omega lives on site, and the unitary variable u is living on link, and we can just sandwich like this. And if you rewrite it by using this A, you can show that this is exactly the same as gauge transformation at continuum level up to higher order fraction.
Okay. Can you say again, what does this free index a mu means? How is there a free index in the exponential? Just go back to the previous slide. What is e to the power I a times a mu? Why is the mu index free?
So this mu. This mu means, so mu means direction from 1, 2, 3, 4. So there are 4, so starting with x,
Oh,
there
so you're
are
defining 4 different u's.
Yes,
Okay.
4 different u's, yes. There is no sum related to mu or whatever. Okay, and we can easily show that this is actually correspond to gauge transformation in continuum theory. But this is symmetry at discretized level because we multiply omega and omega dagger here. And for this, we multiply omega and omega dagger. For this, we multiply omega and omega dagger. But then, because action is actually trace of a product of link variables. This link variable, this link variable, this link variable, this link variable. And the first one becomes like omega u omega dagger. Second one becomes omega u omega dagger. But then omega dagger and omega can just cancel. So this is invariant at this discretized version of gauge symmetry at discretized level.
Why were the last 2 daggers?
Here and here.
Yeah, why are these last 2 ones daggers?
Okay, good. I had to explain it. So you by when we say u dagger mu x, when you say dagger, this is living on this direction. So you can imagine this u is a very short Wilson line connecting this point and this point.
Right.
And this, we can call it u. So I would say, when I say, so this u dagger mu x, this is just literally dagger of this u. But you can imagine u dagger is u minus mu starting from this point.
Okay.
And so if you take u dagger, you can imagine this is a Wilson line going to the opposite direction.
What's the meaning of A minus mu?
Where?
You said that I can think of U dagger mu as U minus mu.
Ah, okay, so mu is this direction, minus mu means this direction.
Right.
And so this unitary link variable has the direction.
Okay.
And without dagger, it's going to this direction, so it increases 1 unit of mu. And with dagger, it decreases 1 unit of mu. You can imagine u times u dagger is 1. But going to one step here, go back one step here, then it cancels. So gauge symmetry is kept at the discretance level. And it's apparent that this actually does not have a continuum rotational symmetry, but it has 90-degree rotational symmetry. And it has discrete translation symmetry, and charge conjugation parity, and so on. And these symmetries are kept at the discretance level. And these exact symmetries are good enough to control relative correction. And you are guaranteed to get right continuum limit. Okay? Because the continuum limit has to respect the exact symmetry at the discretance level. And a priori, of course, it's not 100% clear if continuum translational symmetry is restored at continuum level, but you can actually do some perturbative calculation to show that. So important thing is exact symmetry at the discrete levels guarantees gauge invariance, translational invariance, rotational invariance, and so on in the continuum limit. But what happens if the gauge symmetry is explicitly, not spontaneously, but explicitly broken at regularized level? For example, we can just introduce momentum cutoff. But then we cannot really keep gauge symmetry. Then, as I have said, when we are interested in low energy, long distance physics compared to lattice spacing, and so we integrate out the higher frequency mode, short distance mode. But when we do that, relative correction which breaks gauge symmetry can appear because we don't have such symmetry at regularized level. And to kill such problematic term, we have to add counter terms which cancel such contribution. And but how can we determine such counter terms? In principle, we can do that, but we have to add many terms, and usually we cannot calculate the coefficient of such term. So we have to numerically determine it, and have to fine-tune parameters. And maybe you can play with one parameter fine-tuning, but if you have 3, 4, 5 fine-tuning parameters, it's very hard. It's practically impossible. So we end up with this kind of fine-tuning problem. This is the reason why we must preserve symmetry exactly, and we should use clever action, like Wilson's bracket action. And the problem with the technical challenge in super mills on lattice is exactly the same thing. And actually, we can easily give no-go theorem for exact supersymmetry on lattice. So SUSY algebra contains infinitesimal translation. And I don't really know how to change this infinitesimal translation to discrete translation. And if we accept infinitesimal translation is part of the algebra, then it's explicitly broken by lattice, by construction, because lattice just can keep discrete translational symmetry by construction. So in this is
I missed this step. Why didn't you have the same problem with Young-Mills?
in the Young-Mills case also, okay. So in Young-Mills, translational symmetry is broken to discrete counterpart, but that discrete counterpart was good enough to control the continuum limit. But so in this case, if we can make sense of SUSY subalgebra, make sense of a discrete version of SUSY algebra, if we can replace this to be discrete translation at regularized level, and if we can make sense of it. If that's good enough to control the continuum limit, it may not be a problem. But I don't know how to do that.
So the issue is that this anti-commutator is non-trivial and that there is some translation generator on the right-hand side.
Oh, yes.
If you didn't have the translation generator on the right-hand side of any of these anti-commutators, then you wouldn't have this problem.
No. And actually, that's what I will mention for now. So anyway, so from this, it's clear that it's impossible to keep all the supercharges exactly on lattice because we cannot get right-hand side. Then SUSY breaking relative correction appear in general, and the continuum limit cannot be taken without performing fine-tuning. But of course, still it is possible to preserve part of the supercharge, part of the symmetry algebra, which does not contain translational symmetry translation generator. But the problem is if such sub-algebra is good enough to control continuum limit. And the basic breakthrough idea in this field was proposed by Habra Hudson in 2002. So David Kaplan and Ami Katz, at the time he was in Seattle as a postdoc, and Mita Tunzal, he was a student in Seattle. Yeah, so he's reading a book in Dead Sea. And so in Dead Sea, he thought he has to read something on Dead Sea, but he didn't have a book, so I just gave him a Japanese guidebook on Israel. So if you can read Japanese, you can read Israel here.
This was used in this idea.
Anyway, but this is something we have to do when we go as a foreigner when we go to Dead Sea. Anyway, so in principle we can keep a few supercharges exactly on lattice, and they come up with the smart idea to do that. It's very technical, so I don't explain the detail. And they studied if by using such exact sub-algebra of supersymmetry and a few other discrete symmetries associated with that algebra, whether it is possible to forbid SUSY breaking relative correction. And for technical reasons, they could apply this method only for extended SUSY algebra, but they concluded that in 0 plus 1 or 1 plus 1 dimensional theory, no parameter fine-tuning to all the imperturbation. So no fine-tuning is needed to all the imperturbation theory if we design lattice action in a clever manner. And the reason that in these cases argument was, such a strong argument could be made is so 0 plus 1 or 1 plus 1 dimensional theory is a super renormalizable. So possible Feynman diagram which can generate dangerous relative correction are limited. And fewer symmetry could good enough to control it. And in 1 plus 2 dimension, still it's super renormalizable, but it has more diagram, and they are not sure if they could control the relative correction. And there is no definite conclusion, but many people believe that it's impossible. And in 4 dimension, there are many diagrams, and it's just impossible. And the 0 plus 1 dimension is particularly simple. And in this case, actually, matrix quantum mechanics is UV finite. So there is no relative, of course, there can be finite relative correction. But unless we take a very stupid action, actually there is no need for fine-tuning at all. First of all, there is no relative correction. But almost no relative correction. But for the n equal to 4 is also UV finite. But the UV finiteness of this theory relies on cancellation coming from bosonic and fermionic sectors. And if we use lattice, when we apply lattice, that cancellation is broken. So we cannot use the same argument for the n equals to 4, even though it's UV finite. Anyway, so in matrix model case, because of this very nice feature, we don't even have to use supersymmetric action, or we don't even have to use lattice. Actually, we can just fix the gauge, introduce momentum cutoff. That's good enough. and that's very efficient. And also, lattice action can also work, but unless you take very stupid action, it works perfectly fine. In continuum limit, supersymmetry is restored automatically. So we can use a very simple lattice action which can be studied on computer very easily. And in 1+1 dimension, argument is a bit more complicated, but it's also doable. And 2+1 dimension requires fine tuning if we use lattice. So we need some. So there are two approaches. Use lattice and do parameter fine tuning, though it's hard, or we may be able to cook up something else. And probably the best way is to use approach proposed by Mandelstam, Aryan, and Feynman long time ago. And their argument is that they start with the Bernstein, Mandelstam, and Tase matrix model, or plane wave matrix model. And this is the zero plane matrix model plus some deformation term. And this model has a rich structure of a vacuum. And also this model keeps supersymmetry, all supersymmetries, modified version of supersymmetry. And because this is 0+1 dimensional theory, of course, we can easily study it on computer at each fixed value of n.
I guess you forgot the F mu.
No, this is 0+1 dimensional theory, so there's no mu.
You said it's 2+1.
So we start with 0+1 dimensional theory and use it to construct 2+1 dimensional theory. Starting point is 0+1 dimensional, okay? And we embed two-dimensional space to matrix. And this is, we use the so-called Meyer's effect. Okay, so first of all, so we can discretize 0+1 dimensional theory in very easily. And we can take continuum limit at each fixed n. But each theory, this VMN matrix model has a fuzzy sphere solution. Okay, so if you look at the classical equation of motion of this guy, and we just set the gauge field to be 0, x to be time independent, then equation of motion becomes very simple, like this. Okay, so this first term appears from commutator square term, and the two terms appear from flux deformation. And if you take x to be some constant times SU2 generator, which satisfies this anti-commutation relation. So epsilon 1, 2, 3 is +1, epsilon 2, 1, 3 is -1, and so this is structure constant of SU2. Oh, and I forgot to say, but in this model, so originally we had 9 matrices, right? But here, SO9 symmetry is explicitly broken to SO3 times SO6. And we use ABC to denote first 3 matrices, 4 to 9, and small I to denote 4 to 9. Okay. And we look for classical solution in which only x1, x2, x3 are 0, and all others are 0. Okay. And the equation motion becomes like this. So we now only have x1, x2, x3. And imagine x1, x2, x3 are SU2 generators with this commutation relation times some constant. Then you can see that, for example, if you take a commutator of J1 and J2, you get J3. And you further take commutator of J2 and J3, you again get J1. So this part is proportional to JA. So these B are the same. Okay, so this part is proportional to JA. And this one is JA. So for example, if A is 1, B and C are 1 and 2. So this part is, so if A is 1, B and C are 2 and 3, right? So this part is essentially half of the commutator of J2 and J3, which is J1. And of course this part, so when A is 1, this is just J1. So here you always, so from all 3 terms, you get something proportional to JA. And by choosing constant factor appropriately, you can just make it vanish. And you can also show that this solution is actually supersymmetric classical solution of this matrix model. And this classical solution keeps supersymmetry. And this fuzzy sphere can be regarded as non-commutative version of D2 brane. So it's kind of a round up D2 brane made of D0 brane. And you can mathematically, you can actually make a correspond mapping from matrix language to non-commutative space language. You can actually make, by fuzzy, I mean slightly non-commutative version. Fuzzy D2 brane is generated this way from D0 branes. And there are various different fuzzy sphere solutions, because here we just require that the commutation relation to be SU2. But we can have spin 1 representation, or spin 1/2 representation, or spin 2 representation. And we can have various fuzzy sphere solutions. And some of them correspond to 1 plus 2 dimensional super MLs, and some of them should correspond to M5 brane, and so on. And by taking appropriate large N and small mu limit, actually we can realize 1 plus 2 dimensional theory from matrix model. So if you're interested in the blackboard, I can explain later. But anyway, the point here is, so first we have a continuum 0 plus 1 dimensional theory. And we just pick up classical solution of that theory, which keeps supersymmetry. And this N is actually like lattice size. But at finite level, once we take continuum limit at 0 plus 1 dimensional theory, SUSY is already restored. So we have a supersymmetric regularization. So analytically, we can show that at least to all the perturbation this way, we can get 1 plus 2 dimensional theory without parameter fine tuning. This was an argument by Mandelstam, Sheikh Jabari, and Van Ramsdonk. And they argued not just 1 plus 2 dimensional theory. They even claim that they can make a 6 dimensional L equal to 2 comma 0 theory this way. And by using Monte Carlo simulation, it should be possible to check such conjecture. So by using such a numerical method, it should be even possible to study 6-dimensional theory non-perturbatively. But if what they say is correct. And if we want to define 3 plus 1 dimensional theory, we can do something similar. And a historically interesting example is for the n equals to 1 pure super MLs, which consist of only gauge field and gauge in. And in this case, of course, we cannot keep supersymmetry, but if we keep chiral symmetry on lattice, then in continuum limit, actually, chiral symmetry guarantees supersymmetry. Because only dangerous term is mass of gauge, and the mass of gauge is forbidden by chiral symmetry. So by using some other symmetry, we can take a correct continuum limit. This was proposed by Kaplan and Kaci-Veneziano. And at that time, people didn't know how to keep chiral symmetry on lattice. So people couldn't really use this strategy to study supersymmetry. But in 90s, David Kaplan or Herbert Neuberger, these people found a nice formulation of chiral symmetry on lattice. And actually, such technology is now very standard in lattice QCD community. But using that method, actually we can start define for the n equals to 1 pure superMLs. And last year, I found some paper from Germany who claims not exactly this method, but applied a similar method to study for the n equals to 1 pure superMLs. And it seems that such approach is actually working. So now it's dynamical simulation of this theory is definitely within reach. People are actually working already and getting good numbers. And in the case of for the n equals to 4, situation is a bit more complicated. Such simple argument doesn't work. And the method I'm pushing is again hybrid formulation, like Mandelstam and Shekijabari Feynman's approach for three-dimensional theory. I skip the detail, but I claim that two-dimensional theory can be regularized by using lattice without fine-tuning. And we can make something like this model, but a two-dimensional version. Two-dimensional VMN-like model are known, and we can regularize such two-dimensional theory by using lattice technique. Then combining lattice technique and the fuzzy sphere technique, actually we can show that 4n equals to 4 can be obtained without using parameter fine-tuning. And we already have good theoretical understanding about that, but simulation cost is big, so we haven't tried yet.
Are your simulations there in 2D or in?
So what we do is simulation. Action itself is two-dimensional superMLs with some deformation term. Okay, and n is always fixed. So first we study some vacuum of n equals to 3 theory, SU3 theory, and take continuum limit. And we study some vacuum of SU4 theory and take continuum limit. And if you study, so we take continuum limit for various values of n. But then actually n is a regularization parameter for the other two dimensions. And then we take large n limit. That large n limit corresponds to the other continuum limit for the other two dimensions.
Okay. And the reason the computational costs are high is it?
Firstly,
large n or because?
Large m, and also compared to 0 plus 1 dimension, 1 plus 1 dimension is already more expensive, and so on.
I have a question. So you can do this trick, this fuzzy sphere trick only in the large n limit?
So fuzzy sphere relates matrix model and non-commutative space. And in order to relate non-commutative space, finite in theory, and non-commutative space at finite volume. And in order to take commutative limit and large volume limit, we have to send m to infinity. So in order to get the continuum commutative theory, so usual theory on commutative space, we need large n.
Where does the superpotential look like on the lattice?
Say it again.
How does the superpotential look on the lattice?
Superpotential. I mean, actually, it's just like this. So we just have but it's not a QCD first of all. So it's a maximally supersymmetric theory. So we just have usual kinetic term for scalars, commutative term for scalars, and we also have F mu nu squared, and we have psi bar d psi. That's it.
Okay.
And if you add some other potential, of course, action become more complicated, but the SUSI is broken to lower number. And the reason why I don't really care about that case is actually for supersymmetric QCD, we don't yet know good fine-tuning free formulation. And also some people from Japan argue that large n limit can be described by using so-called Eguchi-Kawai reduction mechanism, keeping supersymmetry. Or I don't know if they are still pursuing it, but at some point, Heckman and Feynman, they proposed some other matrix model approach would work. And also, Carterol, Joseph, and some other people are pursuing the four-dimensional lattice simulation. Oh, there's a very smart postdoc in Berlin, David Scheik. I forgot to write his name, but probably Carterol, Joseph, and Scheik are pursuing it as a main driving force. But in their case, they need the 3-parameter fine-tuning, and I'm not sure if their approach can be successful or not. But at least there is attempt, and they are constantly reporting the progress, so it may or may not work. And so I want to apply, such regulation method and Monte Carlo technique to study superstring theory. And for various reasons, and especially cost. I said various reasons, but actually cost is the only reason, in fact. But I want to concentrate on p equal to 0 case. Okay, so this duality, but p equal to 0 case. And I'm not sure if I still have 10 minutes, but if I start talking about it now, maybe I have to stop in the middle. Maybe I should postpone it to tomorrow.
Okay, you have 15 minutes.
15 minutes, yeah, but once I start, there's no good
there's no stop.
place to stop.
Oh, we can,
Yeah, the only advantage is maybe, I can show joke paper before Blaze leaves, but
I'm happy to.
okay.
we can start.
Anyways, we can. Should I start or I can just continue tomorrow?
Okay, we'll check good place to stop and get some questions maybe, and then you can
Okay,
continue
then
tomorrow.
maybe just just continue 10 more minutes. Okay, so fine tuning. So I just explained the fine tuning problem, but in 2D, 3D, 4D, at the theoretical level we solved it. And at the simulation, so we actually did performance simulation in 1 and 2 dimension, and we have shown that this approach can practically work. Especially, actually, all these arguments are perturbative level. So we knew that fine-tuning problem is not really a problem to all the perturbation, but maybe at non-perturbative level it can be a problem. But at least numerically, we don't find any problem. And same problem, there are many papers, but as I have seen, somehow just forgetting about phase, that simple approach work, at least practically. And so these two are the biggest theoretical problem, but by now I would say there's no problem for many important theories. And I say that fine-tuning problem doesn't exist, but it's true only for certain theory. For example, for maximally supersymmetric theory, there's no problem at all. But we don't know how to regularize supersymmetric QCD. Anyway, so we study this case, and p equals to 0, it's cheap, so we can go to continuum limit, we can go to very large n, and we can do very precise test. And so we want to do precision test at p equals to 0. And this is the model. So this is the Lagrangian, and this is the dimensional reduction of for the n equals to 4 to 0 plus 1 dimension. And it's the other type 2A black 0 plane near the fifth limit. And as I have explained, this lambda has dimension of mass cube. In two-dimensional theory, coupling constant has mass square dimension. In three-dimensional theory, it's mass to be 1 dimension. And in four-dimensional theory, coupling constant is dimensionless. And because the coupling constant has a mass dimension, this set the scale of the theory. And typically we say, okay, we just fix lambda equals to 1. But the meaning is we always secretly multiply appropriate form of lambda to dimension for quantity to make them dimensionless. And when we say to fifth limit, if it were four-dimensional theory, we fix lambda to be order 1, fix temperature to be of order 1, the energy scales like n squared, but the counterpart here is this combination scales like n to the 0, this combination scales like n squared. And we consider that limit. And black hole mass should correspond to energy of the matrix model, which is defined by taking the derivative with respect to beta. So take free energy. So log of z is free energy, and take derivative with respect to beta. This is the standard definition. And we can, by using gravity dual, we can calculate these numbers. And this is a leading supergravity part. And these are alpha prime correction. And we can determine these power because we partly know the alpha prime, detail of the alpha prime correction. But we know some part, we don't know some part. So we know that alpha prime correction should be absent for alpha prime to the 1 and alpha prime to the 2 order. But the first collection appears at the alpha prime cube order. And then just from power counting, we can show this power. And then alpha prime to the 4th is absent, then alpha prime to the 5th should appear again. And then by power counting, we can calculate this coefficient, this power. However, we know that alpha prime cube term exists in higher derivative correction to supergravity, but we don't know the coefficient. We don't know the detail of that correction, that part. So we cannot determine this coefficient. So this is the situation in superstring theory side. But anyways, so we know some information, so we want to reproduce it. We want to see if these powers, or especially this number is the most important thing, can be reproduced from Monte Carlo gauge theory. And this is the simplest and the most basic quantity. And I think numerical simulation is the only practical tool to approach this problem.
Well, can you determine also B and C, or you don't?
Numerically, we can determine from gauge theory, but from string theory side, nobody has succeeded. And when I have shown numerical value, we determined from matrix model. Several people, I remember 2 people, Sine and Postop. Both are really good at hard calculations. They said, oh, it should be possible to do it. I will calculate it. And it was a long time ago, and I don't hear anything. That means it's a very hard question. If they cannot do it, that's not it. Of course, we should try, but it's not straightforward. At least if they cannot do it, I cannot do it. Okay. So this is a supergravity prediction. This is a high temperature limit determined by part of the calculation, and this weak coupling behavior and strong coupling behavior should be somehow interpreted. And before showing the result, okay, so probably after explaining the flat direction, we can finish. We have first, actually in this model, we have one more problem, which is called the flat direction problem. So this is the action, and this is a potential term. But this potential term is 0 when xi and xj commute. So if all matrices are just diagonal, there's no potential term. And classically, eigenvalue can just become a very big value. Quantum mechanically, if we don't have this part, fermion, and we just have bosonic theory, quantum correction leads that flat direction, and eigenvalues just bound. But if we have supersymmetry, then very often with the supersymmetry, contribution from bosonic sector and fermionic sector cancel, right? And we can show that this flat direction is not lifted, even at quantum level. So path integral is actually just divergent. It's not well-defined theory. But this is not a bug, and it's actually a feature. And intuitively, we can understand eigenvalues of 9 matrices as a location of these ND0 branes in 9-dimensional space, intuitively. And black hole is a bound state of eigenvalues. If there are many particles bound in a small space, it becomes heavy, it becomes black hole. But of course, we can imagine something like a gas of D branes. And such fates should also be described. And this matrix model contains all these components, not just about one black hole and gas, but it can contain 2 black holes or 3 black holes or whatever. And we have to restrict the path integral in order to single out one black hole configuration. Okay, that's a situation we want to study. So we have to tame flat direction and have to extract the black hole. And this is actually practically the hardest part of our study over 10 years. And in string theory, this black hole is actually stable when G string is 0. And the G string is 1 over n in field theory side. And so in game theory, if duality is correct, we would imagine if we take large n limit, bound state becomes stable. And of course, we cannot send n to infinity, but if n is big enough, bound state should be stable. And actually, we can observe it numerically, but even before going to numerics, actually, we can easily understand it by drawing some picture. So when we have one black hole, okay, all the eigenvalues of all the diagonal elements are sitting close, but then strings connecting the zero brains are light. And actually those, so I said n, these diagonal element describe the location of the zero brains, but the ij component of the diagonal element describes the open string excitation between ith and jth brain. So strings are short and they are excited a lot, and those strings connect the zero brains so that they can form bound state. So you have n squared, n times n matrix, all entries are excited, and you have n squared degrees of freedom. But when one of the d brain is emitted and go very far, over diagonal strings connecting this d brain and other become very long, heavy, and decoupled. And in terms of matrix, this row and column become 0. But you have just n minus 1 squared degrees of freedom. But in order for such emission to happen, you can imagine, if you just imagine a classical dynamics, for example, in order for this to happen, 2n degrees of freedom suddenly become 0 together. It's very rare, entropically suppressed process. And once it happens, then there is no force. This particle can go anywhere. But in order to escape from others to sufficiently far, some rare process should happen, and such process has some phase space suppression factor, exponential minus n. This is just a difference of entropy. Entropy is n squared versus n minus 1 squared, not so on. So large n, if we take large n limit, our configuration becomes stable. So practically, if we plot trace x squared over n integrated along the time direction, we can see that when n is 4, it starts with 0 and go up, and at some point it diverges. But if we increase n to 8, it becomes more stable and eventually diverges. And then when n is big enough, for example 16, we never see tunneling. We can actually see such pattern. And this is actual plot. And for example, we plotted the trace x squared actually divided by n as a function of Monte Carlo time. And if this happens, so at least one of the eigenvalues is going up. So this is not a black hole. We don't want this. We want something like this. And actually, this was a joke paper for you. So I think it's familiar. You know what this plot means. You don't know?
Who are you talking to?
You. Because you're leaving tomorrow, so I have to show this joke. I think you know it.
You've been telling me about it a couple times.
Yeah, right? So this is standard of Poor's 500 and the Nikkei stock average. So it's a stock market in Japan and the United States. Okay, so Bank of Japan is smart enough. So they detected the asset price bubble here, and they tried to kill the bubble, and they killed the economy itself. And we are peacefully living in black hole. And the Federal Reserve Bank tried to kill the bubble, but it's still going up. Anyways. So for black holes, of course, evaporation of black hole is very important, interesting process. So eventually, this is more interesting. But as a start, we are interested in Nikkei stock average, okay? And we study Nikkei stock average. And if I continue, actually, I don't have material for tomorrow. Of course, I can cook up something for tomorrow, but should I continue or now? It's
I
time
think
to end?
it's time now. I think
Okay.
Maybe let's thank Masanori. Let's see if there's any questions on the stock exchange. Okay, I don't see any immediate questions, so let's name Masanori again.